hardly can hear myself. Okay, so Adam Levi is an old timer in the institute. He started as an undergraduate student and worked in my lab and improved the performance of the lab tremendously all over the years. And then started his master's and worked on the effect of CO2 on live ventricular that yielded also a publication. And that represents only a very small part of the work that he was doing during that time. And then he started his PhD. The PhD started in 2019, very close to the corona. And after the corona, we had the 2023 war and then 2025 war. And so, like Yaffa Yaakoni, Adam Levi is the student of the war. That was not very simple, especially since Adam is living in a kibbutz, Netzel Sireni, which probably did not receive any bombing, but all the alerts were there. Okay, that was not very simple. We had lots of difficulties because of these conditions. The corona was particularly difficult because much of the work that Adam needed to do was involving work in the lab with organisms, and that was not very simple to make. At the end, I'm very happy. Maybe I should also mention that during his master's, he was also in charge of the computing in our institute, just on the side. And one more thing is that many of our connections overseas, mainly in the UK and Germany, we've also hampered a lot because of the situation, the war situation. So, despite all this, Adam will present today parts of his PhD thesis, not all of it, and I let him give the talk.
שומעים? נפלא. Okay, good morning. My PhD is on the aspect of the global carbon cycle from a stable isotope to carbon sequestration. Most of the work was done with Jonathan and other collaborators from the university and from Germany and Russia. In the chapters of the PhD, we have the first chapter of the delta-18 temperature calibration of Operculina ammonoides. This was done with Amalia Davis and Jens Fiebig from Germany. The second chapter is on carbon dioxide sequestration by aragonite dissolution and carbonic anhydrous. It was done with David Avnir from the chemistry department and Andrei Drozov from Sochi University. The last part is on the source of oxygen isotope in the foraminifera skeleton. This work is still in the making. We finished all the experiment. Now we just write and work on it. The first chapter, calibration of delta-18 temperature equation for Operculina with lab culture experiments. We start from the Eocene. In the Eocene, we had the nummulites that would spread across all the Tethys Ocean. If we will go to today, we can see all the nummulitic limestone that are in this area. Most of these areas are reservoirs of oil and gas as today, like this one. The nummelites from the Eocene are very large foraminifera. You can see in this picture. We have them a lot also in Israel. In about 30% of the land cover of Israel, you have inside of it nummulitic limestone. Oh. מקל, כן. נעבוד עם מקל. Okay. From here. Also, we found a lot of nummulitic limestone in Egypt. We have the big pyramids that all of them are built from the nummulitic limestone. And why the nummulitic so important? If we go to the Eocene, we can see the hot house and the warm house. That we have the temperature from oxygen isotope, that most of it from planktic foraminifera. And again, we have also the CO2, the atmospheric CO2 concentration, that this is from boron isotopes and deep benthic foraminifera and some other proxies. We can see the correlation between the high CO2 and the high temperature of the Eocene, and also the low CO2 in the glaciation. And today we are here, around 420 ppm. So in the Eocene, it was a warm and high CO2 period from 65 million to 35 million ago. David Evans, in his work, show from magnesium-calcium ratio and clump isotope on nummelites that the estimation of the temperature in the Eocene was a little low, mainly in the polar area. So how can we measure something about the nummelite to know what to do with them? We cannot take nummelites and grow them in the lab and do a temperature calibration for them. So we can go to the next relative that we have now. It's the operculina ammonoides. Operculina ammonoides is a large benthic foraminifera that we have in Eilat and across all the Indian Ocean. It's mainly in the photic zone from depth of 10 to 50 meters. And it's very easy to collect them. You just take a little bit of sand and you have a lot of foraminifera inside of it. So what we did, we took foraminifera from Eilat, live foraminifera, cultured them in 4 different temperatures, in duplicates. Every week we exchange the water and measure oxygen consumption or production, pH, alkalinity. We estimate the growth from the alkalinity depletion, and all the forams during the experiment double their weight. So we have a lot of new skeleton that calcified through the experiment. No. Okay. We did a measurement of the isotopic composition in Germany, in Goethe University. The measurement done by Amelia Davis and Professor Jens Fiebig. They measure delta 18, that's 13C, and also all the clamp isotopes of the 47, 48, and 49. We have another paper on the clamp isotope in the operculina with them. We calculate the new delta 18 in the skeleton according to this equation that takes the total mass of the foraminifer, and we have a control group that we killed in the start of the experiment. So we have the old delta 18 of the skeleton, and then the ratio between them is the new delta 18. From all of this, we got this equation, this Palo temperature equation, that is fit nicely with the points of the foraminifera and the temperatures. When we put this equation with other paleoceanographic known equation that a lot of people work with them, we can see that this is our equation, the blue line, and we have also here a mollusk and we have here mollusk, we have here planktic foraminifera, we have another deep benthic foraminifera, that's the Virgulina. We have inorganic calibration, and also another shallow benthic, that it's the Marginata. All the lines sit together, all the calibration equation, but then we have this new equation of Deron, that this is, it's not a problem, but it's something we needed to think about it. Deron, in 2019, together with Copeland and after Gray, did a lot of work on two places that it's Devil's Hole and Legato Basso. It's, these two places are small water ponds inside the caves that inside of them there is a precipitation of super slow precipitation of calcite that, according to the physics, it's in equilibration with the water. And then what they are saying that all the other calibration that done until today are not really not equilibrated with the water. Like we have a shift of 1.5 to 2 per mil that is 7 to 8 Celsius degrees from the real equilibration value. But it's not making a problem with the calibration, with the empirical calibration of the foraminifera or the other biogenic calcites. Another thing that we have, that the perculina and the nummulites also are high magnesium calcite. When you add magnesium instead of calcium to the lattice, you get stronger bonds. And heavier isotopes love stronger and stable bonds. So you get, if you have more magnesium, you get more delta 18 inside the shell instead of, but it will also shift you from the equilibrium to equilibrium. But what happens is that when you have magnesium, you get closer to the equilibrium value of Deron and Copland. So after we did the calibration, we took the data from the numolite of David Evans, and we calculated again from the delta 18 that he measured what will be the temperature that we get. And somehow it sits very well, very nice, one against the other. But it's circular argument because the calculation of the delta 18 of the water was done by other pilot temperature equation of loosened areas from 83. That it's similar to ours. Summary. Yeah. So we got new calibration for the delta 18 temperature equation for percolaina ammonoides. That it's analog for the Eocene numolites. This is the equation. The calibration is almost identical to previous calibration, also of planktic foraminifera, other benthic, and inorganic precipitation. Despite all of this, we have the claim of Deron Copland that it's not in equilibrium, but it's really doesn't matter because we do empirical calibration and not, we don't care of the equilibration with the water, just we care what was the temperature. So we will go to the second chapter, it's a little more complicated. Carbon dioxide sequestration experiment by argon dissolution and catalysis with the enzyme carbonic anhydrase. This was done with David Avnir from the chemistry department and Andrei Drozov from Sochi University. We can go again to this figure and see that okay, this was, we see that the connection between the high CO2 from the Eocene to the high temperature. And we can see that when the CO2 is going down, also temperature goes down. Today, we are here in this area. So if we look at today, we can see of the last millennia, and from the last 60, 70 years, we have a peak of CO2 that is going up from the industrial revolution. And we can see also the same trend in the temperature that is going up. The main thing that we need to do is to take CO2 down. How we can take the CO2 down? We can take it from the atmosphere. It's not so easy to take CO2 direct from the atmosphere. It's not practical. It's take a lot of energy that makes more CO2, so it doesn't help us. What's make it that we need to take the CO2 from the source of the CO2. That is the power station and the power plants and the industry. Many engineers suggest that we can just do carbonation. That is, we need to precipitate calcium carbonate. But when you you precipitate calcium carbonate, you release CO2 to the atmosphere also. The proper way is probably to dissolve calcium carbonate. We're not the first one that think about that. We have Rao and Caldera and others, and also this was the work of Eyal Wurgaft that published a year ago, I think, with Noga Moran work. So why concentrated sources? We have the industry and the electrical industry also and the transportation, because transportation is also going to electrical. So around 75 of the global CO2 emission are from the industry and from electrical. If we look on the power plants, you have between 5 to 15% of the flue gas is CO2. In the steel factories, we're going up to 20 to 30%, and cement production is 25 to 30%. That is most of the CO2 that emits from China. It's from cement and steel industries. So we need to capture it from the start instead of let it go to the atmosphere. How this will work? We will dissolve CO2, we will dissolve calcium carbonate together with water and CO2. What will give us a solution that have a lot of calcium and bicarbonate inside of it. This reaction product are very stable, and we can just dump them to the ocean, and it will increase the alkalinity of the ocean. Okay. When we add enzymatic inside of it, so we take carbonic anhydrase, we catalyze the reaction of also the capture of the CO2 to the water, and also the dissolution of the calcium carbonate. We used in our test in coral aragonite, and we test the kinetics of this effect in fresh water. Some basic definition, we have the dissolving organic carbonate. That's all the organic carbon species. It's all the inorganic carbon species. It's the sum of the CO2, bicarbonate and carbonate in the water. Alkalinity and omega, that is the ability of the solution to dissolve calcium carbonate inside of it. In nature, this thing is work fabulous. When CO2 is entered to the water, and then it's changing to a bicarbonate, you have CO2, it's a calcium carbonate accumulation or calcium carbonate dissolution. It depends on omega. If omega is below 1, you get dissolution. If it's above 1, we get precipitation. What we want to do is to dissolve calcium carbonate. What it does, it's also change the pH, it's take it to higher pH, and also it's reduce the DAC inside of it. Our experiment system is very, very simple. We take we take calcium carbonate and mix it with water. Then we do tumbling of it for 20 cycles per minute. This is what it makes it. The particles are always in suspension. In the end, we measure alkalinity, pH, and conductivity. When we measured alkalinity and conductivity, we also took some samples for OES for calcium concentration. We did calibration between all the methods to see that we don't really need to measure calcium all the time because it's fresh water, so all the calcium that dissolve is translate to conductivity. So we just can measure conductivity and We know the alkalinity, and we know how much aragonite dissolved inside of it. Okay, the effect of CO2 concentration. We use with the free CO2 concentration of 100%, 50%, and 5%. And you can see the dashed line is the control without the carbonic anhydrous. The solution is very much linear. When we add the carbonic anhydrous to catalyze the system, we get something like 2 to 4. The reaction is faster in 2 to 4, in factor of 2 or even 4 times. We also test the surface area. If we change the size of the particles, how its effect on the dissolution. And then we got some problems, because if you go beneath 150 microns, you move from the from reaction control to surface control. Then you have more surface, but you don't use the carbonic anhydrous, is not effective. And also you get aggregation of the samples inside of it, so you cannot retain the particles in suspension. So we stick with the 100 to 500 micron size. Another thing that we did, we add more or less calcium carbonate to the system. And this was effect of direct surface area. You get more surface area. All the reaction is faster. And again, if you add carbonic anhydrous, it's even faster. And you can dissolve more calcium carbonate per time. Carbonic anhydrous. The catalysis of this enzyme is very significant for this reaction, because if you go to more industrial processes, you need to do it much faster, because time equals money. And so even with low concentration of carbonic anhydrous, we can double the reaction time, and each doubling of the carbonic anhydrous concentration, it's also add 25 more. It's shorter the time of the reaction, 25%. The problem is that carbonic anhydrous, it's not cheap. So we need somehow to find a way to recycle it, or to make some synthetic carbonic anhydrous. After we had the many experiments, we started to model this system. The model is based on paper on the work of Wigley, Parkhurst, Plummer, and Busenberg from the USGS that worked on it from the 1960s, I think. They did a lot of experiments and got the solubility product of aragonite, and also all the kinetic constant of the dissolutions of calcium carbonate in different shapes. So I built some models with FreakC and MATLAB, and started to run them, and the fitting to the experiment was very nice. without carbonic anhydrous and also with carbonic anhydrous. And then we started to work on the model to see how much CO2 we can really remove from the start concentration in the reaction. And what we got, that in the 5% CO2, we can easily remove 90% of it. So if we start with 50,000 ppm, we end up with 5,000 ppm, that it's not going to the atmosphere. In the 50% and 100%, we can reduce the CO2 by 10 to 20%. And also we can see the models that with the CA and without the carbonic anhydrous, and that we get in the 5%, almost 90% of it, we can take out and move it to bicarbonate. So we started to look on lower concentration of CO2, and we put the line on remove 60% of the starting CO2, and so we get to 50% CO2 is the most, it's the highest concentration that will work in the system. If you get more, you need to start to capture again the CO2 that you have and make it again. And because power plants go up to 15%, this is what we aim for. Then we took all of this stuff and put it on the FIS diagram. In the first diagram, you have the DIC, the total alkalinity. You have lines of equal pH, and the color is the saturation state of the aragonite in the water, in fresh water. The red line is the model. The dots are the experiment in time from the start to the end. And with the 5%, we finished the experiment in omega of 1 because we cannot dissolve more aragonite above 1 if we get to 1. And in pH of 7.4 and the alkalinity and DIC of around 2,800. The ocean itself has alkalinity of something like 2.5. So we have higher alkalinity, but we have low pH. So we can dispose it to the ocean, and it will not create precipitation of calcium carbonate inside of it. If we look on the up to 15%, we can see that still we get higher alkalinity and also higher DIC, but the pH is lower, it's around 6.9, and still if you mix it with seawater, nothing will precipitate from it. It will be stable and will be not reactive. Summary. Carbon budget. For every molecule of sequestered CO2, we get 2 units of bicarbonate. One of them is coming from the CO2, the other one is coming from the calcium carbonate. This will eventually remove between 80 to 90% of the initial CO2 that we start with. This reaction product can safely be discharged to the ocean or to rivers and from there to the ocean, and nothing will precipitate with them. So we don't have a CO2 release from these solutions. This system is very low energy. If you go to mineral carbonation of silicates or something like this, you need a lot of heat and a lot of energy for the reaction. Carbon dissolution, it's quick and it's working in ambient temperature also. And the CO2 is locked in the bicarbonate. This would just increase the alkalinity of the water, and at the end will also help for the ocean acidification because it will rise the alkalinity. It will increase the alkalinity. I'll say thank you to my advisors, Jonathan Erez and Jonathan Goldsmith, that is not here, it's in Vienna. My committee, Boaz Luz and Dani Chernov. Our collaborators, Somalia, Jens, David Avnir, and Andrei. All the Institute of Earth Science technicians, staff that needed to work with me across the years, and all the other people and students and colleagues. In the end, for Apocalypse Horseman, my wife and my children. That's it. Thank you very much.
Questions?
זה הצגה נגמרה. כן.
מה, אתה מדבר על, so what is the cost for grinding rock, the energetic cost for such small?
You don't need to grind the rock because you have a lot of grind rock from other process. In every limestone quarry, you have a lot of debris that you just can take from them. They don't need it.
In this size?
Yeah. This size and smaller also. And you can also use bigger size if you have bigger reactor. You just need the right ratio between surface area to water.
There was a study showing that dolomite is more effective than limestone.
If you look at the KSP of dolomite against limestone or aragonite, it's almost the same. It's in this. If you go to big process and big reactors, it doesn't matter. So you get another 5 minutes or less. So just build a bigger reactor.
So I have a question. If you, basically you're talking about grinding up rock,
Yeah.
okay, and reacting it. So why do you use aragonite rather than calcite?
We use coral aragonite because we had coral aragonite. And the coral aragonite have a lot of surface area because it's of the porosity. It's not just broken limestone. You have in size, let's see if I have it here. You can see that you have the BT of you have the surface area of the particle, but if you look of what is really the reactive area in regular, it's around, if I remember correctly, in corals it's something like 100 more than in regular stones because of the porosity.
What is the effect of pressure on the reaction?
We didn't check it. We wanted, but it didn't happen. So I really don't.
If pressure is favorable, you can, instead of doing it in a reactor, you can just push it into the rocks.
Yeah,
Higher pressure built in, temperatures.
yeah. You have a paper from 1993 that they tested, and it's working on carbonate. But then you want to also take the water out because you need all the time to replace the water inside of it.
Yeah.
So you can work on closed reactor with pressure of water, but it's really don't. It's another energy that you need to enter the system. This is the most low energy system that you have. Just tumble it in a big concrete crack, and that's it.
So your starting solution is always distilled water, or do you also use solutions that you can find more natural?
No, we use the distilled water, but if you go to rivers around the world, most of the rivers are with low alkalinity and low calcium, so it's almost the same. You have the highest alkalinity, the highest calcium concentrate that you have in most of the rivers is below 1 millimole. That in the ocean you have 10 millimoles of calcium.
Right, so let's thank our speaker. Thank you. וכמובן,